Hello and welcome back to 30 minutes of problem solving a day, where I basically live solve stuff and I do not edit it, and I do 30 minutes a day, as the title of the series suggests. And we actually made it to day 2, isn't that crazy? We got 2 whole days of this. And hopefully I get to actually premiere these videos so that you guys could chat with me while they're actually playing, and it might be fun. So why don't we just get into it. We're just going to go where we left off on the AMC 12A 2011, starting on problem number 16, I believe. So, what do we got? We got each vertex of convex polygon ABCDE is to be assigned a color. I should probably put on my 30 minutes so I don't have to keep checking my recording software. 30-minute timer. Epic. Okay. Each vertex of convex polygon ABCDE is to be assigned a color. There are 6 colors to choose from, and the ends of each diagonal must have different colors. How many different colors are possible? Okay, so we got a pentagon. Oh my god. I know my gons. Okay. And essentially we want ends of diagonals. So essentially this guy has to be different from these two guys, and this guy has to be different from these two guys. Alright. So why don't we just fix the color, right? Let's just say the colors are like 1, 2, 3, 4, 5, 6. So if we put that as 1, then essentially these guys have to be not 1. I guess, yeah. So I guess there are like 5 ways to color this guy, right? And this guy does not impact this guy, so there's also 5 ways to color that guy, right? Then this guy is only impacted by this guy so far, right? So essentially this guy still has 5 options, right? It just can't be whatever this guy is, but then this guy depends on these two guys, right? So essentially if these two guys are the same, then this guy only has 4 options, or 5 options, but if these guys are different, then this guy only has 4 options, so that is annoying. Huh. So I guess we could just do casework, right? So if they're different colors, that means that this guy only has, let's see. Because these guys might be the same color, they might not. Does that matter? Because the set of 5 colors this guy could be is different from the set of 5 colors this guy could be, so that's annoying. Let's think. There gotta be a nicer way to do this, right? Well, what happens if we like set up the 3 like adjacent guys first? So there's like 6 ways to do this guy, 6 ways to do that guy, 6 ways to do that guy. And then if these guys are the same, then this guy has 5 ways, and if these guys are the same, then this guy has 5 ways. Oh, that's a lot of casework, right? Yeah, this is kind of annoying. Could we do like overcounting? So we're overcounting. No, we're not real. No. How else could we do this? I guess what we could do is we could say, there's gotta be a smart way to do this, I swear. Let's see. So if we set this guy to 6, well, yeah, okay, that's for sure. Then if there's, okay, let's just say this guy is different, right? Then there are 4 ways to do this guy, right? And then this guy is also different from this guy, right? So if both of these guys are different from the original guy, then this guy has 4 and this guy has 4. Okay, so that's easy, right? So now we need the case where this guy is the same and this guy is different, right? So 6 times this guy is same, right? So 1. In which case this guy has 5 options, and then this guy is different from this guy, so there's 4 options here, right? Then the other option is just you flip this, right? This guy is the same, right? Then that will be so just this times 2, right? And then basically all 3 of these guys are the same. Then in that case, I mean, it doesn't matter if these 2 guys are the same. The only thing that matters is this guy and this guy are the same. So yeah, so essentially there's 6 ways to choose. All 3 of them are the same, and then the rest is 5 times 5. So we got 6 times 5 times 5 times 4 times 4 plus 6 times 5 times 5 times 4 times 2 plus 6 times 5 times 5. And if we factor out the 6 times 5 times 5, we get like 150 times 16 plus 8 plus 1. And that is equal to 24, 25. So 15 times 25 is, I'm assuming it's 3250, but let's just make sure. 25, 15, 5220. Oh, it's 375. Yeah, that makes sense. Yeah. Okay, so 3750. Hopefully we didn't screw up. I feel like it was less though. I remember. uh oh shoot. It is not that. Okay, hold up. Wait, am I trolling? So essentially, this is if they're both different from this guy, right? Then this guy has four options, and this guy has four options, right? Oh, wait, what? Yeah, that's true. Okay, and then in this case, you got like this guy and this guy are the same, and then this guy and this guy are different, right? So then there's four here, there's five there, and then you multiply by two because you can flip it around. Huh. What did I do wrong? Let us see. Are there any other diagonals I'm forgetting about? Oh, these guys. Yeah, okay. These guys can't be the same. I'm trolling. What the heck? Oh God. Okay. So essentially, these guys cannot be the same. So there's only four options for this guy, right? And then this guy, this doesn't work at all. So in this case, now we can actually do it properly. So it'll be 6 times 5 times 4 times 4 times 4, and then this would be um 6 times what times 5 times 5 times 4 times 2. Okay, so now if we just add these up, we should be good. So 30 times 64 plus 40, right? So that is just going to be 68 times 3. Wait, what? No, 84. Yeah, okay. So 84 times 30, and that is just equal to, no, what? That is way too small. What? Am I trolling that hard? So you got 40, and you got 64, and you got 80. Oh, shoot. Oh my god, what am I doing? 104. I could add, dude. This is so sad. And I can't edit this, okay? We're not editing this. Bro, that's so sad. Okay. 3120. Okay, that makes so much more sense. I forgot about this diagonal. Oh, that's so sad. Pretend that didn't happen, okay? Now, problem number 17, okay. Circles with radii 1, 2, and 3 are mutually externally tangent. Pretend they're tangent. What is the area of the triangle determined by this thing? Okay. So, you basically get... Okay, this doesn't seem too bad, right? They're just, I don't even know which one was 2 and 3 anymore because I drew it so badly. Okay, whatever. So, you got like... I guess it doesn't really matter, so we could just take it out even. So we got our inner triangle, right? And then we basically got our 1, 1, we got our 2, 2, and we got a 3, 3. And basically this is pretty like obvious, like this is a common thing that, actually is it? Never mind. I was gonna say that in circle because like common external tangents are equal, but I don't know whether that's necessarily true. Let's see. I'm pretty sure it should be, right? Like this should be the in triangle. I'm not 100% sure, so let's not let's not assume that yet. So what could we do? We want the area of the triangle that, okay, so let's see. So it's 4, 5, 3, 4, 5. Oh, it's literally a right triangle. I'm so troll. Okay, so 3, 4, 5, right? 3, 4, 5, and we got our 1 by 1 triangle here. Wait, this is just, okay, so if this is like a 3 and 3, oh, we get to use like sine and cosine and stuff like that. So the area of this right triangle is clearly 1/2, right? Because 1 times 1 over 2. The area of this is 3 times 3 1/2 times sine of this angle, right? And that is just equal to 3 over 5 times 3 over 5 plus 1/2 times 2 times 2 times sine of this angle, which is 4 over 5 plus 1/2, and that is the area of the outer triangle. So we got to subtract that from the overall area, which is 3 times 4 over 2, which is 6 minus all that. And what do we get? You guys get to see me do math in real time. A very epic. 27 over 10 plus um, 8 over 5 plus 1/2, and that basically gives us 16 plus 27 is 43 plus 5 over 10, which is 48 over 10, which is 24 over 5. And then, wait, what? Oh, and then you subtract that from 6, so you get 6 over 5, which is D. Let's go. Very nice. They basically did the same thing. That's cool. Number 18. How much time do we spend on those two problems? Oh, dang, that was kind of bad. On the actual content, you do not want to spend 10 minutes on number 16 and 17, but that is okay. Suppose that x plus y plus x minus y is equal to 2. What is the maximum possible value of x squared minus 6x plus y squared? So I'm assuming there's some kind of, like, complete the square thing, because that's usually what those kind of things turn out to be. Okay, so you basically have x minus 3 squared plus y squared minus 9, right? I don't know whether that's useful at all, but let us see. Okay, this is assume that, well, actually, okay, so x is probably negative, right? Because if you want to maximize this, I mean, what? Huh. So x is negative for sure, and y is probably very positive, right? Oh, but x minus y, oh, yeah, okay, that's kind of annoying. Okay. Okay, so x is probably less than y then, right? I'm assuming. Because you want the, like, 6x to be positive, and then in that case we basically have plus y minus x over here equals 2, and then x plus y, do we know whether that's going to be negative or positive? I have no idea. Let us see. Well, okay, so basically what it's saying is that the distance between them plus the sum of the two is, like, equal to 2. So, okay, let's just say we make x negative 1 and y to equal 2, right? No, that doesn't work. Or like 1.5 or something? Huh, the problem is that, like, yeah, the problem is that, like, huh. The problem is that it doesn't have to be integers necessarily, but I'm assuming it probably will be integers. Let's see. Okay, so I guess negative 1 and 1 gives you the right, like, a 2, right? Then, essentially, we could do, like, negative 2 and 0. But that'll get, okay, you could do negative 1 and 1, I guess. Negative 1 and 0 works too, but that's just dumb. I mean, like, straight up, it's just probably, like, you plug in negative 1, so that gives you, like, 16, and plus 1 minus 9 is 8. So if we could be 8, could we get 9 is the question. So essentially, I don't think we could beat 8, like, there's probably no way. But could we prove that is the question. So you want x to be as negative as possible, right? So if x is negative 2, then y has to be negative 1, right? Because then, no, but then that's way too big, because it'll be like negative 4 or something, negative 3, so it'd be, yeah, that's way too big. Well, yeah, okay, so I guess the proof is, right, like, if x is negative, less than negative 1, right, then y has to be, like, within 1 of x, which means that it's also negative, right, which means that, like, the x plus y is going to be, like, greater, like, this first term is going to be greater than 1, which means that they have to be closer together, so I guess that's worse. Okay, let's see. So if you do, like, negative 1.5 and negative 1, that just doesn't work. Yeah, so I'm pretty sure it should be 8. Yeah, okay. 8 is our answer. Very nice. So what did they do? Yeah, okay, so yeah, that makes sense. So essentially, if we could just, like, write out this thing, what does that even do? So in here they're both positive, right? So for, huh, what does that even do? Let's see. Well, I guess, yeah, I guess you could just graph it and then see what is closest. So yeah, that makes sense. 1, -1. What over here did they have? Oh, I see. Yeah, okay, that makes sense. Yeah, they just went through all the cases and that proves it. Okay. Number 19. What else do we got? At a competition with n players, the number of players given elite status is equal to 2 to the 1 plus log 2 of n minus 1, and then the floor of that, right, minus n. Suppose 19 players are given elite status. What is the sum of the two smallest possible values of n? Okay, so the floor of log 2 of n minus 1. So let's just say n is like 2 to the n plus 1, right? Or 2 to the k plus 1, let's say, right? Then essentially this thing is going to be k, right? So you get 2 to the 1 plus k minus 2 to the k plus or minus 1, okay? Which is like, what? Which is like 2n, right? I don't know, let's do. Why don't we just try stuff, right? So we basically want this, let's just say this is, well, let's say we want one less than that, right? Then this basically would drop down in whole integer, so this would be 2 to the k, right? And then this would be minus 2 to the k. And then changing n by like a little bit more down, if you moved it down a little bit more, then it will just be subtracting or like adding 1 over here. Oh, what? It's 0? Wait, what? So if you do, if n is the power of 2, then it's just 0. Okay. Well, that makes sense. Okay. And then, okay, so if you add 1, then you get this, right? If you add 2, then this stays the same. 2 to the 1 plus k minus 2 to the k minus 2. And so on and so forth up till the next power of 2. Well, okay, so 2 to the 1 plus k minus 2 to the k is literally just 2 to the k. So it's 2 to the k minus 1, and then you just do minus 2, minus 3, so on and so forth. So the first smallest value is probably going to be like, it has to be like 32 minus 13, right? If you want to get 19, and then the next one is going to be like 64 minus, minus what? 35? 45? 45, yeah. Right? Okay. So essentially, n has to, okay, so this is like 2 to the k plus 1, right? So if you want minus 5, it had to be like 2 to the 64 minus 45, right? Or plus 45. Yeah. And then this would have to be 2 to the 32 plus 13. And what do we want to find? Well, the sum of the two... No, what? That's way too big. What? Oh, am I trolling? Hold up. Oh, it's literally like 64... Wait, what? Oh, shit. Yeah, so 2 to the 6. Yeah, okay. 2 to the 6 plus 45 and 2 to the 5 plus 13. So that is going to give you 32. Okay, whatever. So 64 plus 45 is what is 109, and then 32 plus 13 is 45, right? So if we just sum that, we should get 154, which is C. That should be right. Hey, let's go. Very nice. That one was kind of cool. You just had to find the pattern, and that was a very cool pattern. All right, number 20. What do we got? How much time did we spend on those? Dang, we're actually going through them pretty fast. Oh, 10 minutes for 18 and 19. That's not horrible. Not can't be that bad. Okay, f of x is equal to ax squared plus bx plus c, where a, b, and c are integers. Okay, so suppose that f of 1 is equal to 0. Oh, I hate these, dude. I used to be so bad at polynomial stuff, so I literally went through the like intermediate algebra polynomial section like 5 times trying to figure it out, but I'm still bad at polynomials. It's okay. Let's see. So we got So obviously like x minus 1 is the root, or 1 is the root, and then essentially we got this stuff. Okay, what are we able to do with this information? So, okay, so essentially we got like a plus b plus c is equal to 0, right? Um, then we essentially got like 49, a plus 7b plus c is between 50 and 60. And then 70 is less than 64, a plus 8b plus c is less than 80, okay? And we're going to find for 100, which is 1, what is it? 100 squared times a plus 100b plus c is between two multiples of 5,000. So what do we got to do? Could we like, could we like add these or something to do something fancy like that? I feel like if we could add them somehow, and then that would work. But essentially, they could only differ by 1,000, right? So we can't multiply them by too much, otherwise they will not be precise enough. So right now they differ by 10, so we had to multiply these by less than 100 or something. Okay. So essentially we got like, okay, so let's just say we have 64x plus 49y plus z is equal to 100,000. Then we got 8x plus 7b plus z, 7y plus z is equal to 100. And x plus y plus z is equal to 1. Okay. So this is just like three unknowns, three unknowns and three equations, so we could solve for it, right? So we get 7x plus 6y is equal to 99. We get 63x plus, dang, I don't know, is my video blocking? I cannot actually tell. Let me move my video over to the other side and we should be good. Okay, very nice. 63 plus 48y is equal to 9999. And then if we solve for this, we could subtract 8 times it, 56, 63 minus 36 is what? 7? 7x is equal to 999 minus 8 times 99. So, really? So I guess like, okay, so I mean this is 99 times 101, so it should be 99 times 93, right? And then divide by 7. That's not divisible by 7 though. What? I mean, I guess. Yeah, okay. I guess it doesn't have to be divisible by 7, technically. 101 minus, yeah, that's right. Okay. And then, what else could we do? Then we could solve for y, which is going to be negative, right? So, 92 over 6. So it'll be like negative 99 times 92 over 6. And this actually is an integer, right? So it's 46 times 33. Negative 46 times 33 is y. And then we basically want z to get this to 1. Huh. That's kind of nasty though. Uh, really? Yeah, that's kind of nasty, but I think we gotta do it. Hopefully I didn't make any stupid, addition mistakes. That would be sad. So 999, that's right, 99, okay. You get these things, then you subtract 8 times that, yeah, you get that. Okay, I don't think I made any mistakes. Hopefully I really hope we didn't. That would be very sad. So, 6 times this would give us 92 times 99, right? Negative that, and then it would be 7 times this, which is 99 times 93. And that, wait, what? Yeah, 99 times 90, yeah, okay. So that does give us 99, okay. And now we just need to find z, and then we are home free, I guess. No, we don't even need to find z, do we? We don't, right? Because z is just this, and that doesn't really give us any equality or anything. We just know that's 0. So we don't even need that. It doesn't even affect us. So we are basically almost there. So we just need to multiply this by 99 times 93 over 7, which gives 99 times 93. Then we add in negative 46 times 33 times 50. Well, and times 10, right? And this kind of looks nasty, but it should be okay. Should be. Famous last words, but that is okay. Let's see. Wait, but we're multiplying by way more. That doesn't really go with a very good bound. Yeah, that's multiplying way more than 100. So it's not going to give us sufficient skinny bounds. Huh. What do we do? What do we do, boys? Well, we needed to be within 5,000, but I still think that's way too big. Huh. 90 times 93 over 7 and 46 times 33, yeah, those are way too big. Well, let us think. Well, yeah, why don't we just try this, and then if it doesn't give us something nice, then we could try something else. So we get that it is at least 10 times 99 times 93 minus 46 times 33 times 5. Could we factor anything? Okay, so yeah, we can factor a 33, so 330 times 3 times 93 minus 46 times 5. So that's a lot nicer. And then we could actually do it out. So 279 minus 230, 49 times 330. What does that give us? 330 times 49. And that gives us 07229. Okay. And then 002113. Okay. 07161. So that's like 3 times, right? But then the upper bound is going to be like way more, right? Okay, let's just figure out what the upper bound is. It might not be that bad actually. So then we actually get like, oh, that's kind of nasty though already. I feel like it should be 3 though. Do we need to check the upper bound? I feel like we should. God dang. Well, okay, so it'll basically just be plus 10 times 99 times 93 over 7 minus 10 times 46 times 33, right? And we know that this is like, well, we don't know too much about that. Okay, yeah, you know, I'm just gonna do it. This is gonna suck, but it's okay. So 10 over 7, or 10, yeah, okay, 10 over 7 times 99 times 93 minus 46 times 7 times 33. We could factor out 33 again. We get 10 over 7 times 3 times 93 minus 4 times... Oh, what? The other side went down more or something? Wait, what? Hold up. Okay, you know, I'm just gonna do the whole thing. So essentially, we get 16170 as one thing, and we get 80 times 99 times 93. On the actual contest, I would literally just put like 3 because this is like 5,000 times 3. But I'm just gonna check it for you guys because why not? It should be fine. Let's see. How much time do we have on our 30 minutes? Yeah, so let's just check it, and then we could call it a day. I'm just gonna stop the timer because I don't want you guys getting annoyed by the thing just in case it didn't turn off my computer audio. Okay, minus 60 times 46 times 33, okay. And then we factor out a 10 and a 33, we got 330. 8 times 99 times 93 minus minus 6 times what? Oh, huh. it flips the quality around if you multiply it by a negative number. I forgot. Huh. Okay. So we actually got to recompute. Oh, that's so annoying. Okay, so essentially we get like 99 times 93 times 7 times 10 minus 46 times 33 times 60, or plus, yeah, plus that, or no, what, minus that, yeah, okay, because that gets moved to that side. All right, and now if we factor out the stuff, we basically get our 33 times 10 times 3 times 93 minus 46 times what? 46 times 6, okay. And now if we just do this out, we basically get 279 minus 276, okay. 3. Oh, so that actually changes it a lot, right? So 990, or 3, yeah, so that just gives a 990, so, wait, shoot. Wait, that actually changes things quite a bit. No, what? That's not right. What? Did I do something wrong? Wait a minute. So we multiply this by negative, right? Then this has to actually go to the other side, right? Yeah, okay. And then, yeah, because if you have like 1 is less than 2, then negative 1 is not less than negative 2, okay. Holy, bruh, that's kind of annoying. And it actually, did I mess up? So minus 46 times 6, okay, and it'll be 3 times 93. Huh, so it actually is only a difference of 3 times 330. That seems low. 990. That's not even enough to be like 5,000 though. Well, okay, let's just try the other bound, and if that is a troll, then I guess we are doomed. Wait, it's literally going to be bigger than this though, so that just doesn't give us enough information to tell. God dang it. Yeah, honestly, I don't think I had enough time to solve this. So we will continue where we left off next time in the 30 minutes of problem solving a day. It'll be very epic. Sorry to leave it on a cliffhanger like this, but I will work on it, and we'll see next time if I can get it. Alright, see you guys next time. Let's do it. Another day 3. Let's see if we can get to day 3. Alright, very nice.